Today we're going to be talking about inductors and inductance. So for this class meeting and Friday's class meeting, we're going to be introducing a new circuit element in each one to our analysis and all that kind of stuff. These two circuit elements, the inductor and the capacitor, are very related to each other. They are what are called electrical duals, and I'll talk about that a little bit more. So effectively, we're going to go into a pretty granular detail with regards to inductance and all of the relationships, so that we don't have to do it for capacitors because they're so similarly related. So today is going to be annoying to talk a lot, and Friday will be significantly less annoying because I'm going to talk a lot less. So do not update my program. All right, so let's start by giving you guys an idea of what a physical inductor is. So I'm going to start with a core. And there are two typical types of cores that are used to form inductors. We have a cylindrical core, and so this is what's going to form a solenoidal inductor. There's going to be more to it in a moment. And then we may also see toroidal cores, where a toroid is just a fancy geometric term for a donut. So these two things in red are the cores of our inductors. And while they can literally be anything, technically including air, it is much more common to see that these cores are made of ferromagnetic materials, because a ferromagnetic material will enhance the energy storage capability of these devices. Okay, so if you take well, we'll get to the coil part in a second. Actually, sorry, getting ahead of myself. Let's talk about the coil part now. Okay, so around these cores, we wind a coil, and this is simply just a coil of wire. Like so. Here we're going to have the voltage drop across our inductor, so that is VL of T, and the symbol for inductance is L. And this is our current, IL of T. And similarly, around our toroidal coil, we might have something like this. Still just wrapping a wire around it. Let's call this VL of T, and this current IL of T, like so. So what I was saying a moment ago before I interrupted myself is that we could literally take a pencil, take a pen, whatever, wrap a piece of wire around it some number of times, and then we would have created an inductor. Okay, in fact, for those of you who are in electrical engineering and go on to take circuits 3, that is literally something that you will do as one of your laboratory experiments, is you will design your own inductor for your system, that simply details or simply involves wrapping a wire around a mandrel, which is just a form to hold the shape, and then measuring the inductance and then making adjustments and all that kind of good stuff. Okay. So these cores have a coil wrapped around them that has N turns. So the number of turns is important. The reason the number of turns is important is, I don't know what you guys' background is in E&M, but let's say, this is just a brief aside thing here, that we have a wire. And this wire is carrying some constant current, I, like so. Anytime we have a wire that's carrying a current, it is generating a magnetic field. And the magnetic field, excuse me, that is generated by that current wraps around the wire. So this is determined by what's called the right-hand rule. So if our thumb is in the direction of current flow, the magnetic field is going to curl around the way that our fingers do. So I'm going to try to draw that. So we would have something like this, trying to draw this effectively curling around the wire, and imagine that all of these loops are of the same size if I were capable of drawing things well. Okay. So why the coils are important is because the coils serve to concentrate those magnetic field lines so that we have what's called a magnetic flux. Okay. Magnetic flux is just the amount of magnetic field that's passing through a particular surface area. Okay. So inside our solenoidal coil, we would have flux lines that look something like this. So along the vertical axis, everything is nice and neat. And then as we go slightly away from our axis of symmetry, they kind of bend and loop back around like so. And it would happen on the other side as well, but that's going to make the picture just too busy, so I'm not going to include that. Well, in the toroidal coil, trying to make sure I'm working, yeah, using the right-hand rule properly, all of that magnetic flux is going to be confined to the inside of the core material. Okay. So I've hit you guys with a whole heck of a lot of things here. Now we're going to finally involve some math. Okay. So we have a current that's causing a magnetic field. When we have lots of turns in our coil, that field gets concentrated to generate a magnetic flux, and magnetic flux and current are related by a quantity called the inductance. So that relationship is magnetic flux whose symbol is the Greek letter phi, and I usually do a subscript B, is equal to our inductance, symbol L, multiplied by the current I that's causing our magnetic flux, or expressed another way, L is the ratio of the flux divided by the current causing the flux, where the unit of inductance is the Henry. Actually, because it's a unit, it should be a lowercase h, my apologies, where 1 Henry is equal to a Weber per ampere. And since I'm relatively positive most of you don't know what the hell the unit of a Weber is, a Weber is nothing more than a volt second. Okay, so this is volt seconds per amperes. Or I guess you could think of it as well as ohms times seconds, since an ohm is a volt per ampere. Okay. Ohm seconds, yes. All right. So in field of electromagnetics, there is a relationship called Faraday's Law of Induction. Okay. Those of you that have had Physics 202, you're probably familiar with this. But what Faraday's Law of Induction states is that a voltage will be induced in the presence of a time-varying magnetic field, or more specifically, a time-varying magnetic flux. So Faraday's Law of Induction, this E right here, fancy looking E stands for electromotive force, which is for our intents and purposes, excuse me, a fancy term for voltage, is equal to the change in magnetic flux with respect to time. And since we know that flux and current are related, we can put this in a more circuit-friendly form as the voltage VL of T across an inductor will be equal to L, the inductance value, times the derivative of the current flowing through the inductor with respect to time. So instead of a simple constant of proportionality relationship like we saw with resistors, we now have a derivative-based relationship that describes the voltage drop and current through an inductor. Okay. This is going to be expression 1. Yes, sir.
Why are you starting to look at the magnetic flux symbol differently the first time and then after that? Like the one in right there at the bottom.
Oh, it doesn't. There. The Greek letter phi, either way, I drew it as a lowercase phi first and then an uppercase phi, but it was phi the whole time. So that was just me forgetting to put the bar on it or not remembering to take the bar off. It's the same Greek letter either way. So, all right. So this is our first relationship. Okay. So we are going to take a look at this relationship, and I'm also going to introduce you guys to the schematic element and all that kind of stuff, or schematic symbol for inductors. Okay. So our schematic symbol for an inductor is this guy right here. Okay. It's a coil because an inductor represents a coil of wire. It's really all it is. So I'm going to define my voltage drop across my inductor having this particular polarity and my current flowing through my inductor having this particular polarity. And over here on the left-hand side, this is a separate thing, so I'm going to do it in a slightly different color. We are going to connect a DC current source. So using the mathematical relationship that I've defined in equation 1, I want you guys to tell me what the voltage drop across the inductor is going to be, because that tells us something about the behavior of the inductor in circuits. So it isn't necessary that you have a numerical value for L or a numerical value for I in this case. Tell me what the voltage is going to be. Zero. Exactly right. So if our inductor current does not change, the voltage drop across the inductor will be zero. Okay. So what does that tell us? in a DC circuit, inductors are simply short circuits. There is no other relationship that we have to deal with, okay? So that's our first important relationship from this expression, okay? The other relationship has to deal, once again, with the rate of change component of the expression, okay? So we're going to look through a couple of examples here, and I'll try to make this as untedious as possible. So let's say that this graph represents the current flowing through the inductor as a function of time. And let's make a graph over here that's going to represent the voltage drop across the inductor as a function of time. And just for the sake of argument, let's make this easy. Let's say that L is 1 Henry. Our current waveform is going to look something like this. So that after 1 second, our current linearly increases from 0 to, let's call it 10 amps. At t is equal to 4 seconds, our current has remained that constant value of 10 amps, but at t is equal to 4 seconds, it starts linearly decreasing until a point where it reaches 0 amps, once again, at t is equal to 5 seconds. So I want us to use that equation 1 and figure out what the voltage waveform across our inductor would look like. So anybody have any thoughts? Yeah, so we're just going to look at the slope. So whenever the slope is positive, we're going to get a positive voltage. Whenever the slope is negative, we are going to have a negative voltage. And whenever the slope is 0, we have 0 voltage, right? So for the time interval from 0 to 1, our slope is 10 amps per second. We multiply that by 1 Henry, or 1 volt second per ampere. And so our resultant voltage should be 10 times 1 is 10 volts. At t is equal to 1, really t greater than 1 plus, so on the right hand side of 1 if we're using math jargon here, our current is now constant, and so the voltage drop across our inductor is going to be 0 until the current through our inductor changes again, which we know occurs at t is equal to 4. Over the interval from 4 to 5, our slope is negative 10 amps per second. Multiplying that by our inductance of 1 Henry gives us a voltage of negative 10 volts. At t is equal to 5 seconds, we have constant current again. this 5 up here and label this as 10 and minus 10, right? So this is what our relationship is telling us, okay? If we have a linear current relationship, so if our current is linearly increasing, we get a positive voltage. If our current is linearly decreasing, we get a constant negative voltage. And whenever our current doesn't change, we get a voltage of 0, okay? So what would happen if I reduced the amount of time that it took for the current to ramp up from 0 amps to 10 amps? So like, let me put it like this. So what if instead of increasing from 0 to 1, it increased the same amount, but in half the time, and decreased the same amount in half the time? What do we think would happen to the voltage? The voltage doubles. What if I keep making that time scale smaller and smaller and smaller? The voltage gets larger and larger and larger until a point where the current is effectively changing instantaneously, right? So what if I had this situation? Let me put the units on here. So what if I had a current that was 0 until t is equal to 1, and then instantaneously changed up to 10 amps? At t is equal to 4 seconds, it then instantaneously dropped back down to 0 amps and then stayed 0. And let me label this. So this is 1 and 4. What would my voltage waveform look like? So I would argue that it would look something like this. At t is equal to 1, I'm going to have what's called an impulse function, infinite voltage. At t is equal to 4, I'm going to have a negative impulse function, or the voltage is negative infinity. Is it possible for us to get positive infinite voltage or negative infinite voltage? Of course not, right? To do so would require a transfer of an infinite amount of energy in an infinitesimal amount of time, therefore violating the laws of physics. So what does this tell us about the behavior of an inductor? The current flowing through an inductor cannot change abruptly because the voltage drop across the inductor is dependent on the rate of change, okay? We are going to use this relationship. Let me make sure that this looks more like 2 ends. So we're going to use this relationship to aid our circuit analysis when we get to transient analysis starting next week, okay? So the current through an inductor cannot change abruptly. I want to be clear about this. The voltage absolutely can, right? So we see an abrupt change in the voltage looking at our first case, right? When we had a linear increase in current, our voltage went from 0 to positive 10 volts effectively in an instant. That is perfectly okay. But our current cannot go from 0 amps to 10 amps instantly. It has to take time. So somewhere you can actually see this happening is with a hair dryer or something like that, okay? So a simple induction machine like a hair dryer, contains a little induction motor and all of that kind of good stuff. If you turn your hair dryer on to high and you unplug it from the wall, what happens? Sparks. Those sparks are because you're inducing a voltage so large that it's ionizing the air as it tries to maintain that current flow. Okay. So that's up. All right. So I think we've beat this first relationship to death. The simple, yes, ma'am. So that is a good question. Technically speaking, you guys don't have to write this down. The total relationship would look like this. In this particular class, we are going to be working with purely linear circuit elements, which means our inductance value cannot change with time. So if our inductance value is always going to be a constant, that part of the total derivative just gets thrown away. It's meaningless to us. So we don't ever need to use that here. In fact, I don't ever use that relationship really at all unless you're dealing with a system in which you're allowing your inductance to change, which means you have to have some sort of mechanical means by which to change the inductance. So like in an electromechanical system, that part will exist, but in most simple circuits, it will never change. All right, so what we're going to do now is we're going to take that equation 1, and we're just going to apply some algebra and rearrange it effectively. Okay. So if we use just a little bit of algebra, what we will find is that the current flowing through an inductor as a function of the voltage will be 1 over L times the integral from -infinity to the time we're interested in of the voltage drop across the inductor, where I'm using these t primes as dummy variables representing time, because t, the time I'm interested in, is in my limits of integration. You could just as easily say VL as a function of x times dx, where you just understand that x means time in that particular case. Okay, so this is just mathematical notation stuff. Now, this is just equation 1 rearranged. Now we're going to mess with it very slightly, because quite often we don't know what the entire past history of the inductor was, right? So in order to apply this equation, we need to know what was going on at the beginning of time at -infinity, which isn't of any practical use. So instead, we're going to break this integral up. We're going to have 1 over L from a time t0 to a point in time t, a VL t prime dt prime plus IL at t0. This is going to be equation 2. I would say 95% of the time, actually much more than that. So anytime I'm practically applying this equation, I'm using that second representation. There will be times when I am going to be deriving expressions that I'm going to use the first equation just for the mathematical simplicity of it. Okay. So this equation also has couple of important implications. The first of which is that an inductor, to some sense, has a memory, because its current value of current depends on its past values of current. And that past value relationship is buried inside that initial condition. I see you guys making faces at me. It's okay. So the current value of the, so the, let me rephrase it. The present value of the current flowing through an inductor depends on the amount of current that was flowing through the inductor in the past. And that's exactly what's described by this relationship. Okay. So we're going to work a mathematical example that kind of illustrates this. Okay. It'll also show you, to some extent, the energy storage capability. So let's say that I have a voltage source. Vs of t, like so. I'll mathematically define it in a moment. Connected to our inductor. And once again, let's make this a 1 Henry inductor. So this voltage is obviously VL of t. And this current is IL of t. Let's say that our voltage waveform, VL of t, measured in volts, looks like this. Sorry, this should just be t. Measured in seconds. And we have a simple situation where our voltage is 0 until some point in time. When it isn't, then the voltage effectively gets turned on. Let's have it stay on for 3 seconds and then get turned off. So let's call this 1 second. Let's call this 4 seconds. And let's call this 10 volts. Okay. Let us also say explicitly that IL at 0 seconds was 0 amps. So we have some information. Effectively, we're saying that the inductor was fully discharged at time t is equal to 0. And we are going to develop a mathematical expression for the current flowing through the inductor, as well as plot what it looks like. Okay. So this voltage can be represented as a piecewise function. We have 0 volts for all t less than 1 second. We have 10 volts for 1 second less than t less than 4 seconds. And then we have 0 volts for t greater than 4 seconds. Is that an accurate mathematical description? Okay, so it's 0 except when it's not. So let's figure out what our current is going to be. Okay, so 4, let's start specifically at 0. So 0 less than t less than 1 second. our current flowing through our inductor is going to be 1/1 Henry times the integral from 0 to t. So the reason why I'm integrating from 0 to t and not specifically 0 to 1 is because I want to get a function out of this thing so that I know how it's behaving over the entirety of the interval, not just how it's behaving at the endpoints. Okay. Times 0 volts dt prime plus our initial condition, which is 0 amps. So what's this going to look like? What's the integral of 0 over any interval? 0. So our current looks like 0 amps from t is equal to 0 all the way up to t is equal to 1. Okay. Now let's look at it over the interval from 1 second is less than t to 4 seconds. IL of t over this interval, still going to be 1/1 Henry. We're going to integrate from 1 to t. Our voltage is a constant, 10 volts. And here we're going to have IL at 1. Okay. So the value of the inductor current is going to depend on what the inductor current was at those previous times, right? Because we have to make sure that the inductor current is a continuous function or we're violating that relationship, okay? So in this case, IL at 1 is obviously 0 amps because we knew that our inductor current was 0 amps over the interval from 0 to 1. So if we perform this integration, what are we going to get? So we're going to have 10 volts per 1 Henry, where a Henry is a volt second per ampere times the integral from 1 to t of dt prime plus 0. What's the integral of dt? Just t, right? So we are going to have volts cancel each other out, and so we're going to wind up having a slope 10 amps per second, and then the result of our integration is going to be t minus 1. So now let's look at what happens for t greater than 4 seconds. We're going to use the exact same equation. 1/1 Henry times the integral from 4 to infinity of 0 volts dt prime plus IL evaluated at 4. Well, it should be fairly obvious that this bit right here is just going to give us 0 amps because we're integrating 0, the voltage. But IL at 4 is going to be whatever we would get when we put 4 into this expression. So 10 amps per second times 4 seconds minus 1 second is going to be 10 amps per second times 3 seconds, or 30 amps, right? So as a piecewise function, IL of t looks like 0 amps for t less than 0. It looks like 10 times t minus 1 for, sorry, this should be t less than 1, because that's what our interval was. 1 second less than t less than 4 seconds. And then it looks like 30 amps for t greater than 4 seconds. So if I were to plot this, that's 1, that's 4. This is time measured in seconds. I would have something like this. So what I have tried to illustrate with this simple example, and there are a couple little problems with it that I'll talk about in a moment, is that the present value of the inductor current depends on the past value. And so we can see that even though we've turned our voltage source off, our inductor is still carrying its past amount of current because there's not anything to, there's nothing in the circuit to absorb any energy that's stored. This is also exhibiting or displaying the energy storage capabilities of an ideal inductor, right? So the fact that it can sustain a current of 30 amps, even after we've effectively turned the source off, means that it has some amount of stored energy. It stores its energy in the form of its magnetic flux, okay? Now, if we did something like this with a real inductor, would it behave like this? No. Why not? Why is it going to drain? So what is an inductor made of? What did we talk about a while back? It's a wire. What do real wires have? Resistance. So over time, a real inductor's energy will get converted into heat if we disconnect it from the source. Yeah. Okay. We are going to mathematically describe that energy conversion process starting next week when we do transient analysis. That is literally all transient analysis is about, is we have had a source in our circuit connected to either an inductor or what we're going to learn about on Friday, the capacitor, and then see how that particular element responds to us changing the circuit by disconnecting a source or adding another source to it or something like that. And because of the relationships we're developing, we are going to be able to mathematically describe exactly how it happens, and we'll match our analytical solutions up with some labs to show that our models are correct. But we're also going to notice something that's very important. It takes time for these processes to happen. So it takes time for our inductor to charge, which is exactly what we see here, right? We turn our voltage source on, the voltage instantaneously changes from 0 volts to 10 volts, but it takes 3 seconds for our current to go from 0 amps up to its maximum value. It would take a similar amount of time for us to discharge this thing as well. So, all right, so we have our current voltage relationship equations, I think, reasonably well defined, okay? I personally much prefer the derivative-based relationship, mainly because I'm particularly bad at integrals. So I chose an example to where I could do it very easily, okay? What we're going to talk about now, excuse me, is the power relationship for an inductor, and then the quantifying the energy storage relationship for an inductor, okay? So if we have an inductor, L, over which there is some voltage VL of T and some current IL of t flowing through it. The power absorbed by our inductor. What do you guys think is going to be? Yeah, I times V, because that's always power. So VL of t times IL of t. We can substitute in our first relationship, which says that the voltage drop across the inductor is related to the derivative of the current flowing through the inductor. And that gives us the relationship L IL times D IL by dt. So technically speaking, we only need to know how the current behaves in an inductor to be able to figure out how what the power absorbed by the inductor is. Now I'm giving you this expression. I would argue probably 80% of the time I use the first just I times V. Unless literally the only thing I knew about it was actually even then I would probably just find the voltage using the relationship and then do it. But I'm just giving you this for completion's sake. Okay. Sorry for going on a tangent there. That's our third relationship. On your exam, this is a usual theory question kind of thing that gets asked. And the mistake that I see students make the most is forgetting that the good old P is equal to I times V relationship is also valid. So don't forget that one. That's the one that you will practically apply most of the time anyway. All right, so that's fairly straightforward because it's just a simple substitution of what we've done before, or excuse me, what we've done before with a simple substitution of a relationship that we developed earlier. Now let's look at energy. So the energy stored by an inductor, WL, as a function of time, is going to be the integral from negative infinity to t of the power absorbed by an inductor as a function of time. I've chosen these particular limits of integration for a reason. At negative infinity, the beginning of time, I feel that I can very safely say that the inductor didn't have any energy stored in it, so I can effectively call that energy level 0. So that's why I'm choosing t is equal to negative infinity for that limit on my integration there. Okay. So now we're going to suffer through a little bit of math. So using our second relationship here, this is going to look like L times IL as a function of t prime times d IL as a function of t prime over dt prime times dt prime. And so effectively, math majors would hate this, the dt's cancel each other out. So I'm changing my boundaries of integration now. So now I'm going to integrate from current to current instead of time to time because those dt relationships cancel each other out. And so my new limits of integration will be IL at negative infinity to IL of t, L IL of t prime, D IL of t prime, and understanding that the current flowing through my inductor at the beginning of time was 0. This gives me the relationship, if my stylus will write, 1/2 L times the square of my current. So this is relationship number 4. So I can express both the power absorbed by my inductor and the energy stored in my inductor only as a function of the inductor current, okay? So when dealing with inductances, knowing the current is the most important piece of information that you can have. All right, you guys are almost done listening to me rant about things for today. You're so enthused. So the last thing that I want to talk about here is combining inductances. So we may be presented with circuits that contain multiple inductors. Sometimes they'll be connected in series, other times they'll be connected in parallel, and we need to know how to make them look like a single equivalent inductance. Okay. So let's start with inductors in series. So let's say that I have some inductor L1 in series with some inductor L2, all the way out to some inductance L sub n, like so. There is some overall voltage drop across all of my inductors, and there is some current I flowing through all of my inductors. We know that each inductor will have its own voltage drop, so I'm going to call this V1, V2, all the way out to V sub n, like so. And I can write a Kirchhoff's voltage law expression that says that V of t, my total voltage drop, is simply the sum of the voltage drops across all of my inductors. V1 plus V2 all the way out to V sub n. I can express all of those inductor voltage drops in terms of that common current I. So that's going to look like L1 di by dt plus L2 di by dt all the way out to L3. Excuse me, Ln di by dt. And since I have a common factor of di by dt with everything, this looks like L1 plus L2 all the way out to Ln di by dt, or an equivalent inductance LEQ di by dt, where LEQ is simply L1 plus L2 all the way out to L sub n. Or in a much more succinct form, inductors in series combine like resistors in series. So I'm going to write that down. Without making you guys suffer through the math and the derivation, how do you think inductors in parallel are going to combine? Like resistors in parallel. Absolutely right. So I'm not going to make you guys suffer through 5 more minutes of calculus and algebra to get the obvious result. All right, so that is enough out of me for today. Just, I guess, as a word of warning with regard to your homework, I'm gonna pull up the web work. I believe there was a couple of tricky-ish things here. So this is going to be homework set number 12, if I'm not mistaken. Nope, it'll be homework set number 11, because we definitely didn't talk about capacitors. All right, so I actually get a whole heck of a lot of questions regarding this problem, okay? Because it's got resistors and inductors and voltage sources and all that kind of jazz. So hopefully you guys can see it. But in the problem statement, what type of voltage sources are all three of these voltage sources? DC, which means all those inductors are just wires. So this problem is really, hey, do you still remember how to do nodal or mesh? Treat all the inductors like wires and then do everything else how you would totally normally do it. It does not need to be harder than that, so stop trying to make it harder than that. Right? Let's look at problem number 2. So we have a more annoying graph like the ones that I've given you guys today. You're asked to find a couple of things here. I just want you guys to be aware that I'm going to start using this notation of time plus and time minus as well pretty soon. So for part A, when it says it wants the voltage the instant before 6.7 microseconds, effectively, you're taking the derivative from the left. So we have an increasing slope, so we should see some positive voltage that is literally just L, which in this case is 34 microhenries, times 13.5 milliamps divided by 6.7 microseconds. For part B, we want the voltage at the instant afterwards. So we're taking the derivative from the right where it's constant, so it's 0. So I just want to make sure that you guys are aware of the nomenclature, the taxonomy that we're using there. Same thing for the power. The energy is going to be pretty straightforward. You just need to be able to read the graph at those particular points because you're given the current. For problem number 3, this is going to be extraordinarily similar to one of your in-class assignment problems, so I'll field any questions you have about that here in a moment. For question number 4, let's see, you're asked to find the input voltage. So that's going to be a Kirchhoff's voltage law equation, right? The input voltage Vn will be the voltage drop over the 10 ohm resistor plus the voltage drop over the inductor. So you'll have to use a combination of Ohm's law and the stuff that we learned today to take the total voltage drop. It looks like you're looking for a function. So just to be clear here, it's not just a simple number. And my best guess is it's going to be a function of, there's going to be one part that's t squared, and there's going to be another part that is just with t, because when you take the derivative of t squared, you're just going to have a t. So anyway, so applying a very small amount of calculus and algebra to do that one. Similar kind of thing here, except instead of applying Kirchhoff's voltage law, you're expected to remember that Kirchhoff's current law is still a thing and use that. So the current IN here will be the sum of the current flowing down through the resistor, which you can find using Ohm's law, and the current flowing to the right through the inductor, which you would find using the integral-based relationship. Add those two results together to get a function, plug it in, and you're good to go. So anything on this homework seem unsurmountable based on the information that I've provided you over the last hour and 7 minutes. All right, so I'm just giving you guys fair warning about these because these next couple of homework assignments, there are a few problems that are particularly nasty. So I'm just trying to make you guys aware of what's going on.